Welcome if you're here. If you can hear me, just say hi in the chat. So I think that's everything going. Let me just make sure that it starts on your side. Yes, it does. All right, so if you're here, please say hi in the chat. This is an interactive live stream, so it's expected that you use the chat as much as possible, even if it's simple things as yes and no. If you don't understand anything, just say you don't know. If you understood, just say yes. Or if you don't understand, say no or don't know. We want to make this as interactive as possible. So if you are here, please say so in the chat, and please let me know you can hear me clearly, or if I'm too quiet or too loud. We have one there. Where is it from? What's going on? All right. Let me just check something. I've put it on LMS. So if you're just joining us, please say hi in the chat, just so that I know you're here. We'll just wait on a couple more people. I already have done that. I sent it about 10 minutes ago. Oh, maybe I didn't put the link in it. Oops. All right, maybe I'll go back and put the link in it. Give me a sec. I thought I put the link, but I might have not. All right, so if you're joining us, just say hi in the chat. It's interactive, so we need your interaction. I'm just checking that I did send the link out to the emails. Yeah, no, I did send the link out. So that's there. Cool. All right, so what we might start with is just a quick chat about the assignment. I won't spend too much time on it unless you want to. We're not going to cover assignment 2 yet. We still haven't done enough to start that, but we can start looking at that over the holiday break. So what we'll do is we'll have a look at the assignment first, and then we'll talk more on the lab for an arrays. This lab's kind of a little bit more difficult because arrays is usually something that a lot of people find a little bit more difficult. All right, so with the assignment, a couple of things that I've seen so far. The big one that I noticed, which is probably one of the most important ones, is the purpose of the program. A lot of people told me that the purpose of the program was to convert from Celsius to degrees and degrees to Celsius, which, given the solution, is a very, very bad way of solving that problem. If we were just doing the conversion between Celsius and Fahrenheit to Celsius, I don't know why you'd have start, end, step size, or any of these kind of things. So definitely when you do your purpose of your program, make sure that it does match your program, and don't make it your description too generic that users will be confused at what it actually does. So a couple of things with the purpose of the program. The big thing here is firstly the user. Okay, so it gives the user the option, okay, to select two different types of tables, table 1 and table 2. And the first table is a, I think it was degrees to Fahrenheit. And the second table was Fahrenheit to degrees. And these tables had a couple of important things. So firstly, it allowed the user to define the starting value, the user to define the ending value, and the user to define the resolution or step size. Okay, it's not the size of the table, it's the resolution of the table. They are two different things. Okay, for example, I can have a picture that's this big, okay, but its resolution could be pixels this big, okay. So it's important that you specify that you're talking about the resolution of the table, not the size of the table when talking about step size. The second thing about the tables that was very important was it was a formatted table, okay? And if you wanted to, you could extend this, but these were the things that I would consider critical for the purpose, okay? Because if you don't explain these, why did you include them? Okay, if you don't include this, why did you give the user the option? If you don't include this, how do we know that this isn't coming from a server or from a file, or that it's all just hard-coded and will create the same table every time? So these are the kind of things we were looking for the purpose of the program. Okay. The implementation part, most people did all right. The implementation, we were just looking for basically something like do while loop for two things, user to select type of table, and if statement to indicate invalid, loops until valid value, and then the if and else, and then for loops. Okay, the implementation, most people did fine, but in terms of the purpose of the program, really think about the purpose, because that's where most people didn't really have a good go at that. And it was worth 10% of the assignment. So do try a bit harder with that next time. All right. So that was the first thing. The second part was the do while loop. I'll skip over the printing the password and your name. I think everyone did that fine. A couple of people forgot the stars, so they lost a couple of marks there, but they at least wrote their name. So I'm trying to remember the question. There was a couple of ways you could do this, and some people use cars, which was kind of a nice solution. But you knew that the user always entered an integer value. We didn't say the limit of that, so a car would have been suitable. But it really didn't matter which integer type. If you wanted to use a long, it would have been perfectly fine. So we had something like int table type. A couple of people are still using camel case. We're using snake case. That means lowercase and underscores. Okay. In terms of variable names, a lot of students lost marks because of their variable names, especially because of one, which we'll talk about shortly. From here, we had a do while loop. When selecting the most appropriate structure, think about the problem. Don't just go, oh, I only know how to do one type, so I'll use that because it always works. If you don't know how it works, ask. From here, there was a variety of solutions inside of this while loop. One solution would be to continue while it's out of range. So while it's less than or equal to 0, or it's going to be greater or equal to 3. And we had table type, and we could put an or in there. Okay, so if it's less than or equal to, oops, I did that the wrong way. Did I? Sorry. If it's less than or equal to table type, and if it's greater or equal to 3. Sorry about that. Okay, so we could have done something like that. We could have used and not like we did in the previous live streams example. There's lots of ways to solve this problem. There's no ideal solution. Both solutions take about the same amount of time. There's no real big optimizations you could do here. Some people forgot about the negative values when they used something like this, and they only checked if it was greater or equal to 3. It's not a huge problem, but something that you need to consider. With signed values, we can go negative. And also there's a 0 even if it was unsigned. From there, we had a scan. So most of you would have used %D. As I said, some people use %C, but it doesn't really make a difference for this problem. What's good this year, I noticed, is that a lot of people are not forgetting the ampersand here, which is really good, because I remember last year a lot of students forgot that. So it's really, really good to see. From there, oh, I forgot the prompt. We would want that, wouldn't we? I'm not going to write the whole prompt out, but I need a bit of room for it. I'm thinking of last week's lab where we doing the scans inside. So we did a printf of some kind and blah, 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 blah. So there was some text in there that said, what did it say? Please select the table you'd like to create, Fahrenheit to Celsius or Celsius to Fahrenheit. I think it was the other way around, but I think you get the point. And then an if statement here, just to do our check. And all we need to do with that is try and recycle our code so that if we know it works in one place, we can definitely use it in another place, just like that. Okay. Try and get used to copy pasting. It's not a bad thing in coding. If we know it works well somewhere else, you're better off using something that's well known and works rather than something that doesn't. And then from there, we'd have a printf. Now, some people did the whole thing inside of a while loop, and that solution is perfectly fine. It just makes the problem less modular and harder to test, but perfectly fine solution. And if you did that, you would have got the marks for logic as well. If you used a while loop, we didn't take marks off, but we just put a comment there to encourage you to try and think about the logic of the problem a little bit more. And if you had something similar to this, maybe a different condition here, yeah, you've really thought about it well, and so that was perfectly fine. Does that all make sense? I don't think, given the people that are here, I don't think this is too big of a deal. So I'll let you say yes, no, maybe, speed up, go to something else, go over it again, don't know, anything. As I said, we want to use this chat. All right. From there, we then had our if and else. And this is where the small mistakes came in. Actually, not the if and else. The if and else, there wasn't any small mistakes. It was more with the for loops that there was mistakes. So if table type was a 1, else it would have been the second table. And let's just have a look at one table because it's fairly repeated. And I'll talk about some of the common problems that some of the students did. I'm trying to remember what this part was. Yep, okay. So as I said in the previous video, it's a good idea to limit scope. And by limiting scope, we actually can limit the domain of our problem. So this is like a sub-problem. So whatever happens here shouldn't have anything to do with anything outside. And it means that we can name everything in relation to the domain between these braces. A lot of students made the mistake of doing something like this. They'd call their variable start temp. Considering that for the same amount of characters, you could have changed this to a non-generic name. It makes little sense why you would call this temp rather Celsius or even Cell. For the same amount of characters, this adds a huge amount of information to our domain compared to temp. And it reduces confusion between the two scopes. Okay? So if you've got the option, always try and find a name that represents the domain best. Okay? So we had start cell, end cell, and the last one is also important. If you had size, size is wrong. Size would indicate end minus start is size, which, okay, that's size. It's not step size though, okay? So if you had resolution cell or step size cell, I would have been fine with that. But it's not actually the size of the table, okay? If you had n divided by start divided by step size, then you could have the size in terms of, what's it called? How many things are printed. Or if you had size in terms of n minus start, then you would have called it size. But it's actually the step size. From there we have, I think we had a whole bunch of printf, scanfs. Now, a couple of places where some of the students made mistakes here. Some of you had %f in the first table. it should have only accepted integers, and it says that on the document. Those that limited the scope, most of those students got this correct because you couldn't use a float in here and you would have got an error. And this is the great thing about limiting scope, is that if you try and do the wrong thing, the compiler tells you, no, you can't use the %f here. All the ones you've got are %d. And so that's the great thing about limiting scope, is you're helping yourself by letting the compiler tell you off. Okay. All right. So inside of here for this one would have all been %d. Okay. From there we get to our for loop. Now, when we talk, and you can have a look at the standards, we do have some names that all programmers understand what they mean. And they include things like A, I, J, and K. They include things like FP, the file pointer, and stuff like that. And with these ones especially need to be used carefully. Now, these are always going to be indexes or indices, either by multiplication or by square brackets. Okay, so either by multiplication or square brackets. Okay, so they should only be used as indexes. You can do this problem using indexes, but most of you didn't do it that way, and it is fairly complex to do it that way. So really in this problem, you shouldn't have really used I if you do it the way that I'm going to show you. We can also have a look, if we have time later, at how to do it with an index. J should only be used for 2D iteration and should only be used when you've got a for loop inside of a for loop. And K should only be used for 3-dimensional problems. Now, the other rule with these names is that these can only be ints, which follows the rule of index, okay, because you can't have the index of 1.5. I can't get the 1.5 student in a row. Okay, it's either the first, second, third student. I can't get the 1.75 book. Okay, so they should never, ever, ever be a float. Now, for this problem, because this is more about standards and professional programming, if you used I didn't really care too much. I put a comment there if I marked you or I told the others to mark you, and just said, have a think about it next time. If you're using it as an index, so you're multiplying it by some base and adding some offset, then I is fine. Or if you're using an array and you're using the square brackets, then it would have been fine. But if you used I, we didn't take marks off. If you use J, however, we did reduce some marks, especially if you used J and it was a float. Okay? Because we haven't introduced J yet, and you're using something that we haven't introduced, wrong. Okay? We have introduced I, so I can understand that from the lectures you might have got a bit confused about it and you haven't seen much use about it, so we didn't take marks off. But J we haven't seen yet, so there should be no excuse for using it and using it wrong. All right, so I'm actually going to give it a slightly better name. I'm just going to call it current Celsius, and I think we discussed a little bit about this last time. This makes it really readable. Because this isn't an array, I can't really talk about the index of it. But as I said, we can actually do it, but it's a little bit complex. So we'll do it the nice, easy way and use a proper name. So current cell starts at the start. It's going to be going, or it needs some more room, less than or equal to end cell. And, oh, I just broke something. Give me a sec. I can magically make these smaller. Control T. Look at that. Beautiful. All right. And then we can just go current cell becomes current cell plus, actually, let's do a compound statement. You've already covered compound statements, so, and it'll save me some room. Step size. If you don't know what a compound statement is, just, or compound assignment, just say so in the chat and we can cover it. And then we get something like that. Okay. This can be read by any professional engineer or scientist, and they can clearly see what's happening here. They can clearly see the start. Some students left out the start and they set it at the top. The reason we have it in the for loop, yes, we usually declare it, well, with ANSI C, we always declare outside, but we include it inside the for loop rather than just above. Even if we declare just above, is because we want that good documentation. Everyone knows professionally, if they're in engineering and science or IT or whatever, what a for loop is, and they can clearly see where it starts. I've seen a couple of students get rid of this and just declare it beforehand. Don't, okay? It just reduces your documentation. Excellent description there in the chat of our compound assignment. So now we need to use some formulas. And I've got to remember this. So I think I'm going to sneeze. All right, so in here, you could either declare a variable or you could put your formula directly into the printf. Either answer was fine, but if you do it here, you can at least test it. What formula are we doing? We are doing the Celsius one. So what are we doing? We're doing current Fahrenheit. And that formula basically said current Celsius times 1.8 plus 32. I think it was. And I'm actually going to write 32.0 so I don't have to do a conversion. Okay, so that's there, and then we just did our printf, and we'll talk about the printf because this is another area that some students did poorly. With this, you don't need any typecast because we can use, well, not that there. Firstly, we can just specify the literal and do the division beforehand because there's no real need for the computer to do it. We can do it ourselves. And that gets rid of the division completely. But also we know that we need a float in the end. So I'm just going to make all of my literals the type that's going to be stored because I know that the calculation is going to end up as that anyway. So if you know that it's going to be stored as a float, you might as well make them all floats. All right, now with the printf, we needed format specifiers. We needed our width, and a lot of people forgot the width. They knew the precision, but they forgot about the width. We had a width of 3 for the first one, I believe. Let me double check. Yep. And then there was a single space, a line, and then a single space. Then we had a width of 5 and a precision of 2. A width of 5, a precision of 2. Okay. Do we have a space before? No, there was no space before either. Sorry. I'm trying to remember what I wrote. And there's no space after, it doesn't matter. There's a bit of text as well that goes in here. There's a bit of text that goes in here, degrees Fahrenheit, degrees Celsius. And then just obviously reference those, so current and current. Okay. Do I need to make that clearer, or does everyone understand that? If you understood, just say yes. If you didn't understand, say you didn't understand. If there's something in particular you didn't understand, point it out, and we'll speed through this. I think there's no point really going through the second table. The only difference there was obviously we had floats, and the formula was slightly different. I'll give you a minute just to say yes. Cool. All right. Other than that, most of the solutions were pretty good so far. I think the averages are sitting at about. Let me have a look. Yeah, the average is pretty high. It's probably sitting at about 82, 83. The other thing to remember that 90 plus is full marks because of rounding anyway. All right, so let's go have a look at the next lab, because I think that's probably a bit more exciting. Now I've got to find it. Week 6. All right, so we've got functions and arrays. Cool. All right. So, great question. So, if I have, it's really not going to make a huge difference on optimization unless it's in a loop. But it's still a good idea to do it by practice, so that if you do have a large loop of calculations, they do calculate a little bit faster. So if I have float A and I have, let's say I have an int called x. Let's give it a value. Let's give it a nice small value. Okay, it's a 1. And I'm going to go x times float 1 divided by 4 plus 8. Okay, so if we have a look at this, we can see that we're storing a float. We've got integer division, so I've put a typecast there. And everything on this side's an int, but where we're storing it's a float. So let's have a look at this in terms of types, and let's evaluate this together. And you can see kind of why we might want to. Oh, that's not there. Already losing my mind. I divided by I plus I. All right, so first things first is this int needs to be converted to a float. Remember, typecasts have the highest priority. So we get x, well, x is evaluated, so we get 1 times yes, of course. But let's have a look. So we have 1 times float 1 divided by 4 plus 8. From here, we do our typecast first. Okay, so this is 1. We've just evaluated everything. This is 2. Okay, so we've got 1 times 1.0 divided by 4 plus 8. So we've now got I times f divided by I plus I. We now step 3. The next highest precedence is the multiplication. We can't do the multiplication yet because we've got an int on one side, so we have to convert that up to a float. So step 3 is float times float divided by int plus int. Now we can do 1 times 1, which gives us 1.0 divided by 4 plus 8. So from here, we have float divided by int plus int. So 5, we can't do the division yet. We need to convert the 4 to a floating point type. So now we've got float divided by float plus int. Now we can do this division. So we should get 0.25 plus 8. So 6 is going to be float plus int. We can't do the addition yet because we need to convert the 8 to a float. So on this side, we've got float plus float. And then from there, we've got 8.25. So we've got 8, which is a float. And then that gets stored. So let's rewrite that again. And let's have a look at how many steps it takes if we do it using x times 0.25 plus 8. All right, so we have int times float plus, why would I bother putting that? Times float. So step 1 is evaluating the value. So I've got 1 times 0.25 plus 8.0. I need to do the multiplication first. I can't because I need to modify that first part so that it's a floating point. So I have float times float plus float. We evaluate that, so we get 0.25 plus 8.0. So we get a float plus a float. We don't have to do any conversions here, so we get 8.25, and we get a float. And you can see how many operations this took, and you can see how many operations this took. So if this was in a loop where it might actually have some effect, for a single line of code, neither of these you would notice any real optimization. It really doesn't matter. But when you've got a loop that's running 100,000 or 1,000,000 times, then you'll start noticing a difference. Okay. A lot of the times, the optimizer of the compiler will fix a lot of these problems for you. But if you can fix them yourself, you know that they're there. And so it's usually better if you can find them. Does that make sense? And does that demonstrate why one's quicker than the other? Yes, no, maybe. If you understood, say yes. If you're bored, say yes. If you're happy, say yes. All right. So let's have a look at this problem. All right, so let's go have a look at this problem, and we will try and move out of the way. All right. I'm running out of room already. Let's go down here. Actually, let's just start a new page. I started right in the middle. It's probably not a good idea. Let's create a new one. Where's my phone? I just got to answer something on my phone. Cool. All right, so let's get the lab. All right, so in this lab, we're going to have a look at both functions and arrays. These are two big topics, but let's do them together in the lab. I think that's probably the best way to go about it rather than stop. Rather than doing some other examples. Might as well get the lab out of the way. All right, so I forgot the title. Well, I'll write my own title. I've lost the people's. There's the people's. Where's my pen? I'm losing everything. What's the title? Water Pipe System Simulator. That's actually a pretty bad name. Water Pipe System Simulator. All right. In this problem, we want to simulate a water pipe system. Okay, so you can think of pipes with water inside them. Okay, I think that makes a lot of sense. The piping system has multiple pipe segments with varying diameters and at different heights. Okay, so this means that you might have one segment that's very low. Okay, you might have another segment that's very high. So let's say you've got a segment there, you've got a segment there, you've got a segment there. Okay, one's really fat, one's really thin, etc. And we know that water going up versus downhill. We know that water going through a thin pipe versus a big pipe is going to change the pressure and the velocity. Okay? And even if you didn't know that, don't stress too much. I give you all the formulas. All right. So utilizing our knowledge of fluid dynamics, we want to find the pressure and velocity of the water at each section, and if the piping system is valid for water to flow. Because obviously, if we've got little pressure and we tell the water to flow up I don't know, Mount Everest, it's not going to do it. Okay, so we need to know that. To calculate the velocity given the area of two segments, okay, we can use the equation of continuity, which states that an incompressible fluid entering one part of the flow tube must be matched by an equal volume leaving downstream, which makes sense. Like, it doesn't matter how much goes in, you know that the same amount must come out. Okay. So if you've got a little pipe and a big pipe, still the same amount that goes in is going to come out. Okay. This area is some kind of circular pipe, and the velocity we've got coming in. Okay. This is going to be V1, area 1, and then we've got V2, which is coming out, and A2. Okay, so you can do a nice simple example of that, making A bigger and smaller. Okay, so this is what's changing our velocity, and this is in meters per second, and areas is in meters. Beautiful metric system. All right, to calculate the pressure given the velocity, height from the ground of the two segments, the pressure of the previous segments, and the density of the liquid, we can use Bernoulli's equation, which is derived from the principle of the conservation of energy, which we're not going to cover here. All right, so we have this beautiful looking formula. I've always liked this formula. It's something that I've always found really interesting and really cool because it describes it really well. So you've got pressure in pascals, okay? You've got height in meters. Remember, we're talking about a pipe that's going up and down. So we're talking about from the ground. We've got this density, okay, which looks like kind of looks like a P. Okay, it's not a P though. Okay, it's a Greek letter, but just be careful about that. We've got the two velocities. So the yes, it is. We've got V1, V2. We've got plus the density times gravity, okay? Because obviously gravity is going to have some effect. If you're on the top of a hill and you pour water down the hill, it doesn't go up in the air, it goes down. Okay? And you've got the heights. Okay? Now, where are we? For our simulation, pressure and velocity of the first segment is given. Okay, so you know what's coming in. Okay, you always know what's coming in. The fluid is always going to be water. Okay, so no jelly or something weird like that. It's always going to be water. And there's 7 segments in total, each with a known height and diameter that's going to be given by the user. The density of the water is 100 kilograms per meters cubed, and the acceleration of gravity on Earth is 9.8 meters per second squared. I think this is kind of a physics lesson. The pressure given and displayed will be the gauge pressure, which is the pressure in excess of 1 atmosphere. We need to put it into actual pressure to work out Bernoulli's equation. So that's the first thing that we're going to rearrange and rewrite. So as we said, we're given the gauge pressure. So PG for gauge. So we know we need to convert to the actual pressure to use it in these formulas. So we might as well do that now. So we've got PG equals P minus 1 atmosphere. And we know that 1 atmosphere is 101,325 pascals. So we just need to rearrange this formula so that we get P by itself. Okay, so we can just add 1 atmosphere to either side, and we get, my nose is itchy, PG plus 101,325 to get the actual pressure, not the gauge pressure. Okay, so we've already calculated that, which will be helpful for later. We'll look at 2 pipe segments to explain the problem, and then we'll do it with 7 segments. All right, so let's go do that. Oh. All right. So stuff makes more sense when you've got pictures. So let's get a picture. What? My picture isn't that good. I don't know what I was thinking when I drew this. Probably should come back and fix it because it's all pixelated and weird. All right, so we've got some kind of pipe segment there. So what you can see that we've got one segment here, one segment here, and you've got the connection between them. You notice that this segment is 8 meters off the ground, where this segment is 4 meters off the ground. You've got the water, the velocity of the water coming in, which is 5 meters per second, and you got the diameter of the input. You've got the pressure of the input, and we've got the diameter of the output, and what we're trying to find is the pressure of the output and the velocity of the output. So I'm going to have a 3-minute break, and and then we'll go through, solve this by hand, and then we'll do it by code, and we'll have a look at arrays and functions at the same time. And yeah, it'll be really fun. All right. So I'm just going to be back in a couple of minutes because I need to answer something. If you're joining us late or you're still here, just say something in the chat. It really helps me know what the level of engagement is. Let me just for a sec. Mute, unmute. All right, if you're still here, just say something in the chat or put an emoticon of an animal or something. Like a, what have we got? I think a koala. All right. So where were we? Let me rub that off. All right, so we're going to do an example of just one segment, but we're going to see the power of programming when we do 7 segments. We can see that this is going to be a lot of work, but once we get to doing this, what's it called? Once we get doing this with our program, we'll see that it'll be nice and quick and easy. All right, so first things first, velocity is the smaller equation, so we'll do that first. So we'll go steal that equation from here. I can't do that. Why can't I do that? Which layer is that on? Wrong layer. And my printers decide to turn on. All right, so we'll do that formula first. Maybe make him a bit smaller. Is that a unicorn? I think it is. All right, so we'll do the velocity first. So we've got this formula here. So we've got V2 equals area 1 over area 2. And what have we got? We've got diameter. So what have we got? We've got, why does that keep, stop it. So we have V2 equals, now they're circular pipes. So we've got pi r squared 1 over pi r squared 2 times V1. We know that our rate, why can't I write there? I want to write there. Radius equals diameter divided by 2. So we've got everything we need. We also know that the pi's cancel. If you remember this from the previous lab, this is a recurring issue. Now we've got R1 divided by R2, they're squared. So 3 divided by 2 Now, this is in centimeters. We need it in... What do we need to do? We need it in meters. So we'll do that conversion, and we should get 0.015. Okay, that's in meters. And we're going to square that, and we've got 6, which is going to be halved and converted into meters. From there, we also need to times it by our velocity, which is 5. Sorry, why is that printer picking up? And if we calculate all that, we get 1.25 meters per second. So that one's fairly easy. So we can chuck that in there. That one isn't too bad of a formula. The other one is a little bit more difficult. So first things first, we know that the pressure coming in is 90 kilopascals. But we've got a couple of problems here. Firstly, we need it in pascals. And secondly, we need it as pressure, not gauge pressure. And you can see that here, we said before, the information coming in, we get the gauge pressure. So we need to convert it to pressure. And we already calculated this. So if we want the pressure, we just need to add 101,325. We also need to get rid of this K. Okay, so to convert between kilopascals and pascals, we just times it by 1,000. So our pressure 1 is actually going to be 90 times 1,000 to get it to pascals, plus 101,325. Okay, which gives us 191,325 pascals. Okay. All right, now we get to the big formula. Now this formula looks intimidating, but it's actually fairly straightforward. And this is Bernoulli's. So here we have P2 equal P1 plus half times our density, V1 squared plus, not plus, minus, sorry, minus V2 squared plus density, gravity, height. Okay, and then we just plug all our values in. And let me grab the answer, because rather than rewriting it all, you can see what gets plugged in there, but we should get 242243.75 pascals. Now, from there, we've got one more step. We need to convert it into gauge pressure. Okay, so whenever we show pressure on a gauge, we need to convert it back. So pressure gauge 2 is going to be our pressure. So 242243.75 minus 101,325. And this in kilopascals will give us 140.918 kilopascals. So we have 140.9, so approximately kilopascals. So whenever you do this kind of thing, what you've got to ask yourself, does the answer make sense? And so do a mental check. So we've got a fast velocity, we've got a small pipe, and then the pipe gets bigger, so it should slow down. Okay, but we've got all this water pushing down, okay? And the velocity coming in really fast. And so the pressure would go up. Okay, so you can do a quick mental check of that. Now, basically, if we have any pressures that's less than 0, we're going to assume that the pipe segments are invalid because it starts getting complex. All right. Does that make sense so far? All right, just give me a sec. I'll be right back. All right, sorry about that. All right, so now we're going to write our program. And this is where our arrays and stuff start coming in, which is going to be really cool because arrays are cool. All of coding's cool. All right, so are we ready? Where's my pen? I'm not ready. So create a new file in Notepad++, give them a meaningful name, include standard input-output library, and add the main function. Create 2 integer arrays. We're storing the diameters and heights of the 7 segments. So in previous tasks, we have had variables that could store 1 value. But now we're going to look at a data type that can store a collection of values. And this is our arrays. Now, our collection must all maintain the same data type. So, for example, they can all be ints, they can all be chars, they can all be floats, etc. But we can have a collection fairly big, and we will go to very, very large data sets eventually in this subject. But for right now, we'll just use 7. You can scale this problem as much as you like. The other thing that you can start doing, if I put a video out about macros, that's something you can start doing early on as well if you want to check the scale of your problems. But I won't cover that now. But that is there, which is a later video, but you can start doing it early. It's not that hard. All right, so we have int diameters. And we have 7 diameters because there's 7 pipe segments. Okay, and that's the syntax for creating our array. Now, there's lots and lots of ways to initialize, but at this stage, and this is something to be really careful about, we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Now, at this stage, you need to be careful. Remember back to week 2 and 3, and we talked about initializing our variables. And if we don't initialize them, we get some random value. And the reason we're getting some random value is because with C, we don't clear the memory when we create variables, making it really fast, and we can just start overwriting it. Okay, so it means whatever was in memory beforehand, your game, your word, whatever, it will just use that space and continue writing. So there's going to be something random in memory beforehand. If you go and print your array out, and you've just created it, and you haven't given any values, you'll print it out and you'll get some weird values. Okay, so just be aware of that. Okay, be careful. We also need the heights. So we're going to have 7 heights. Now, notice also with the variable names that I haven't called this diameter and I haven't called this height. I've started to use plural language here because I've got multiple things. Okay, so when the arrays try and use plural language, so rather than cat, use cats, age, use ages, etc. Does that make sense? Are we all good up to this point? So this is declaring array. We'll look at how to put stuff in it in a second. All right, so with arrays, we can index them. And this means we can do our two main tasks. And I said this right from the start, and I think this is something that I find a lot of courses don't focus on, and I think it's extremely important because any task you're doing on a computer can really be brought down to this, which is storage and retrieval. Okay, so we can store stuff into our array, and we can retrieve stuff retrieve stuff from our array. So to store something in the array, it just means that it's going to be on the left-hand side. And if we're retrieving something, it's going to be in the right-hand side of some assignment. Or it might be as a function argument or something like that. So if I wanted to store, say, something here in the array, I can reference my array, then use a square brace, and then I could store, say, a 4 in there. I also need the index. Now, indexes start at 0, okay? And start from the left and go to right, opposite to binary that starts from the other way, okay? So I can put a 1 in there, and I can store a 4 in here, okay? Because it's on the left-hand side, I've got storage. Now, from here, okay, what you need to be really careful of is the only time you should see a 7 between these square braces, okay, or the size of the array, is when you create it. After this point, only 0 to 6 is valid, because you can see quite clearly that they're the valid indexes. Now, C won't tell you off, rather it will crash your program, okay? So just be aware of that. And we'll see that, especially when we get to dynamic. For retrieval, so let's create an A variable. We can put it on the right-hand side, and we could retrieve, say, this value here, okay? Diameters. All right, if that makes sense, let me know. I'll be right back. I've just got to sort something out. I will. Sorry, I'll be back in about 8 minutes or so. I've just got to sort something out. Sorry about this. I'll just say a 10-minute break, okay? I may be a little bit quicker. Just need to sort something out really quickly. And then we'll continue, and we'll go through the whole of the first lab. Let me just mute this as well. All right, sorry about that. I am back. Who is still here? If you're still here, just say in the chat. Sorry about all that. I just have to organize something quickly for my home. So we've seen our storage and retrieval, but now we're going to have a look at filling our array, which is one of the common operations that we do with arrays. And it's a very common operation that we do quite often. Ugh. So what we're going to do is we need to first prompt the user, and we need to do this because I think I forgot the mute. Okay. Oh no, I'm not muted. That's okay. All right, so we're going to print to the user, and we're just going to say enter the diameters. Okay. And I might put a new line there as well. Okay. Even with arrays, we still need to ask the user. The other thing that I might mention to the user, because for this task it is important, I might mention that it's in centimeters. Okay. Now, this is the important part. So when we're getting something, there's no scanf to get a whole array. Now, what we need instead is our for loop. Our for loops have a really beautiful relationship with our arrays, and so we'll see them combined very often. So we're going to do for. We need to declare I. Okay, and this is an excellent use of I because we're using it to address every index of our array. So I goes to 7, I plus plus. So you will see this quite commonly. We start at 0, we increment by 1, and we go to the end of the array. Note, there's no equals here. Okay, it's not less than or equals because we don't want to get to 7. We only want to get from our valid range, which is 0 to 6. Then from there, we can use our scanf as we have done before. We're getting ints, so we can use %d. And we still need to use our ampersand as we have before, and we're going to scan in our diameters, and we put an I in the square braces. So this means that the first time we go through the loop, we store the diameter 0. Next time we go in the loop, we store the diameter 1. Next time we go in the loop, 2, 3, 4, 5, 6, and then we don't go any further because it's not equal to 7, it's less than 7. Okay, so we can see here quite clearly that this is a great way of getting stuff from the user. Now, in another video we put the printf inside of the for loop so that you can ask the user, enter the first segment, enter the second segment, enter the third. It depends on the problem. If you want the user to enter a big list, then you can get them to enter a big list, or you can constantly prompt them every time you go around the loop. Are we good so far? Let me grab this. So if we're good, put an animal in the chat or a yes, and then we can continue. Awesome. So for the next part, it's pretty much copy and paste, except for we're not doing diameters this time. We're doing heights, and they're in meters, I think. Yeah, meters. Into the height, meters. Your prompt can be slightly better than that. I'm just being quick. And we've got heights, and they're ints as well. So we don't have to change much for the next part. All right. So now we get to the next part. And this is a part that is important, and I've thought about changing this a couple of times, but I think it's important because it checks that you actually understand the problem and have read the problem. Okay. We said that so the next step is create two float variables to store the initial velocity and the gauge pressure. Now, we basically know how to create two variables. Okay. The first one's our initial velocity. Okay. Now, the second one is the gauge pressure. Now, we know from our example here that our gauge pressure is our initial pressure because that's what's initially coming in. Okay. So you should make that connection there, that gauge pressure and initial pressure are the same thing. Okay. So you could call it gauge pressure or you could call it initial pressure. Either names are fine. I'm going to call it initial pressure. Okay. Either name would be perfectly fine. So you could call it gauge pressure or initial pressure. They are the same thing. We then request these from the user. So we've got a printf plus scanf combo times 2. Okay. Please enter the initial velocity, get it off the user. Please enter the gauge pressure, store it in the initial pressure. Okay. Create 4 new variables, okay, such that we have our current velocity and we have current pressure. Now you can see that this naming I've slowly tried to introduce to you in the assignment. And the reason that I did it in the assignment is so that this doesn't come too much of a shock to you when you see the word current. Okay. So it's going to be the one we're talking about right now. And we're going to say that the what happened there? Previous velocity is going to be our initial velocity, and our previous pressure is going to either be our gauge pressure or our initial pressure. Now, these two variables are going to have the same value: initial velocity, initial pressure, previous velocity, previous pressure. Now, why we've done that is to differentiate them, but when we go to calculate, we already know this, so we're going to calculate this, and we're talking about the previous. Okay. So when we go to calculate P2 and V2, we need to know the previous, which are our initial ones. When we get to the next segment, we're going to be looking at the previous ones. So let's just have a look at an example. So let's say I've got a pipe segment, that's a really ugly pipe segment. Okay. The current will be here. The previous will be here. Okay. Then when we go to the next segment, this current will become the previous, and this will become the current. Then when we're looking at the next segment, this will become the previous, and this will become the current. Okay, so we're just moving across such that the previous is always one behind. All right. We then do a print, and we print the first segment to the screen. Okay, print to screen, first segment. Okay, because that's given by the user, we don't have to do much. When you do that step, just go down the bottom and have a look at the output to get the right formatting. Now, this is very important. All right. This is your chance to shine. Write the first part of the for loop for this. Add a for loop to loop through the 2nd to 7th segment using I. What would be right? And while you do that, I'm just going to fill my drink up. Haven't got any answers. What's going on? All right. Chat's being a bit quiet. So as I said, this is meant to be interactive. If you don't know, just say don't know. So we want to go from the 2nd to the 7th. So what we've got to remember here, and this is where a lot of students make a mistake, is that the 2nd is index 1, and the 7th is index 6. Okay? So we need to be careful about that. A lot of students get a bit confused by that. I know that it is weird and a bit strange, such that we are doing this. But we're doing 7 segments. How many segments are we doing? We're doing 7, aren't we? Yeah, cool. Cool. All right, so we're going to do a for loop. We're going to start at we're not going to start at 0. We're going to start at 1. Because we've already done the first segment, we don't need to start at 0. We're going to go I less than 7, I plus plus. or you could do less than or equal to 6. I prefer less than, but if you like it the other way, it's up to you. It really doesn't make a difference. It's still readable. All right. So what we're going to do now is we're going to stop and we're going to start creating some functions. So what we're going to do is we're going to go right back to the start of our code. So somewhere over here, let's just say over here. And right at the top, we would have had int main. Okay. And we should have had something like hash include standard io.h. Now, what we're going to do above that is we're going to introduce function prototypes. So previously in the labs, we've been using functions constantly. Okay, we've used printf, we've used scanf, we've used getCar, we've used how, we've used fmod, we might have used fabs. We've used a lot of functions, but they're not our own functions. So we're going to write our own functions, and we're going to need to tell the compiler that whilst we're in main, functions exist below main. And to do this, we use function prototypes. Now, the advantage of this is that we don't need to order our functions. We don't have to worry about the ordering. If you declare your functions above main, they may work or may not work depending on the order that they're written. With function prototypes, you don't have to worry about that. And so in this subject, we'll always use function prototypes. So the two functions that we need, don't worry too much about what's inside them. I'll let you watch the video on functions so you can understand in a little bit more depth what's going on here. But we'll focus on the main things here. So we're going to have two functions, one called calculate velocity and one called calculate pressure. And we're probably going to run out of room. No, stop. Arr. Calm down. Why is this being silly? All right, so we're going to calculate velocity, and basically on the left-hand side here tells me what I'm going to return from my function. So I'm going to return a float, meaning that the information that I want to get from this calculate is a single float back. Same with the pressure, I want a single float back. Then on the inside of these brackets that I'm about to write, I'm going to put the types of information that I need in. Now, I've already worked this out, so we'll have a look at these when we actually write the function. And you can just write these for now without knowing what they are. But we can tell from just looking at this that I need, for calculate pressure, a lot more information to solve that problem. For example, if I said to you, write me a function that adds two numbers up. And basically, you'd have some function called add numbers up. And let's say there's two. Then you'd have two things here separated by commas, and you'd have the return type here. So if I said the function accepts and returns an integer, then you'd have two integers here, and you'd have an integer here. Okay, that's the basic concept behind functions. But as I said, there's a video that we can talk about in more depth. Now, below main, so right below main, we're going to add two functions. Now, I've already written these for you, and I will leave it as a task for you to go through these and understand them. You'll note that I've put some comments in there. Haven't put a... I might actually change that. So usually with functions, you should have a function description. Maybe I ask you to do that. Oh, yes, I do. Cool. All right, so you've got two functions here, and part of the question, it gives you the functions, but your task is to write the function descriptions. And you're asking, what are the function descriptions? Well, if you go to LMS somewhere, where's LMS? So if you go to LMS and you go up to resources and you go onto here, you can see what a function description is. So brief description of the function, description of its arguments, so the information passed in, and the description of what's returned, and any notes or warnings. Now, there's no notes or warnings that are needed for this one. So it's just the three things here that we need. Okay, and that's part of the task. I hope I put that in there. Sure, I might update the marking guide for that. All right. So you need to go through these. We've gone through the formulas already. So you can see that the radius is the diameter divided by 2, and we divide it by 100 to convert into meters. Same here. Okay. I don't need to describe that dividing by 2 gets me radius because of the naming here. Previous radius squared, current velocity. So you can refer to the formula above. As I said, there should be a description here, and you're going to add that description. The pressure, you can see that we convert pressure to pascals, and then we add 1 atmosphere. The previous pressure becomes the current pressure. The current pressure, we just chuck it in that big long formula. We've got the density of water here. Okay, we've got gravity here. Okay, so you can see these comments are getting rid of all the ambiguity, and then we convert it back to kilopascals by subtracting 1 atmosphere and converting to kilopascals. Okay, and then we return our pressure. So that's part of the task here. Now, I don't want to spend too much time on functions unless you've got a specific question about them. There's some really good videos there that go into the depth of how to create these yourself. But right now, what you need to know is basically you've got a model that looks something like this. Okay. Data coming in, okay, which is the data coming in is going to be this red part, and the data coming out is going to be this green part. Okay, so that's the type of the part that's coming out, and the return is the actual returning of it. And the stuff that's inside of this box is all this. Okay, so that's all there. Okay, so understand what's passed into the function. Just like your printf, just like your scanf, just like your other functions, you pass something in and it does something. Okay. All right. So from there, we can go back and we can start calling these functions. So when we want to return something from a function, we're always going to have assignments. Now, a lot of students do this wrong. So current, they get very confused between calling a function versus declaring a function. When we're calling a function, we never mention the types. Okay, so we're going to call our calculate velocity, and we're going to pass in our previous velocity, and you'll notice here there's no types here. Okay, I don't say float previous velocity. I then need to pass in my diameter of the previous section, so I minus 1. And that's perfectly fine because I start at 1, so I can't go less than 0. If I had -1, then it would have been bad. From here, I also need to pass in my diameters. It's diameters with an S, I. And then semicolon. So when you're calling, just keep in mind that that is slightly different. You're going to do the same for pressure. And then what you need to do, once you've done that, is basically you need to check if the pressure is valid. Okay, so to do that, all we need to do is an if statement. As I said, if it's less than 0, then so if current, so this is current pressure, is less than 0, then what we do here is we print a message saying it's invalid. Okay, print F invalid, %D, the segment number, etc. And then from there, I'm also going to set I to 7. Why do I set I to 7? Because I don't have to break, and it means that I still have full control of my for loop, meaning that if I need any cleanup code or if I need to trace this, I still can. And then the else, we're going to do a print. And that print is just going to be a formatted print to the screen of the segment number, the current and velocity. So you can see that here. Okay, so you've got the velocity and the pressure, velocity and the pressure, velocity and the pressure. So you can see that on the screen. And we also need to do this if previous velocity becomes current velocity. Okay, because we're going into the next segment, and as I said, we have this continuation where the previous should always be behind the current. We've got previous pressure becomes current pressure. All right. I have one question. In the output shown, it doesn't have the statement less than the initial gauge pressure. Really? Shit. Yes, it does. Right there. Initial velocity, speed, velocity. Yeah. Into the first segment in meters per second. Velocity is measured in meters per second. Enter the water's gauge pressure in the first segment. Okay. We print it out to the screen because we've just read it. The velocity is 5 meters per second, and the pressure is 90.000 kilopascals. So we know this is gauge pressure. Okay. So it does ask for the velocity or speed, and it does ask for the gauge pressure. Okay. So I'm using a bit of different language here. What about steps 8 and 9 then? Create 2 to store the initial velocity and gauge pressure. Well, I need somewhere to store that 5, and I need somewhere to store that 90. Add the printf that requests the initial velocity and gauge pressure. Enter the water's speed or velocity. That's the first printf. That's the scanf. Enter the water's gauge pressure. That is step 8 and 9. Those 2 steps, those 4 lines there are step 8 and 9. Yeah? Okay, I'm just using different language to make sure that you understand the problem. And the fact that the way that we talk to the user is different than how we talk to the programmers. Okay? And there's a whole heap of different tests there. The last test is really important because you need to check that it's invalid. All right. Sorry I went through that a little bit quick. I've got something going on which I need to sort out. So I might leave a little bit early this time. And we can have a bit of a longer session next time. I don't think there was many questions anyway, and we didn't have that big of an audience. But hopefully that was helpful getting you through this question. I do recommend the videos, and then you can have a look through functions and arrays in a little bit more detail. One of the links might not work, but you can access it from the YouTube. I'll fix that up when I get a chance a little bit later. Thank you for your time, and hopefully that was helpful in clearing up any doubts. The other thing is that some of these values might be slightly off. I need to double check them tomorrow because this lab I've updated some of the stuff inside, but the output was the same last year, and I might have been using a different server where the values might be slightly different. So if you're getting values that are slightly off, don't worry about it. All right. Thank you. Unless you've got any last minute questions. Awesome. All right. So try and watch those other videos if you get a chance, and I will see you soon.